Now, since you understand, if like I said, if you really want to understand beta distribution, you need to add the idea of integral definition of a beta function and a non-integral definition. Okay. Now, beta distribution. Take a look at this. That's a beta distribution. We use beta distribution to model random variable in the range of 0 to 1. Let's think about the random variable that can be in the range of 0 to 1. Proportions, rate. Maybe you want to talk about infection rate. Okay? You know, infection rate is a random variable. Why is it a random variable? Because it changes from time to time. What about vaccination rate? What about poverty rate? Does that make sense? Now, if I'm interested in industrial chemistry, if I'm interested in the proportion of crude oil that will be converted to gasoline, it is not all crude oil that will be converted to gasoline. Or in economics, you are interested in the proportion of income that you spend on food. It is not all your income that you spend on food. So it's going to be between 0 and 1. So if I really want to have a probability distribution that can, explain your certainty in proportions, in rates, because why do we have a certainty in it? Because it changes over time. The vaccination changes over time. The poverty rate changes over time. How am I going to know the poverty level? If you really want to investigate maybe a poverty alleviation program of a government, you can conduct a survey. Okay, in the survey, you'll be able to identify those who are living below a poverty line, and the probability, if we now, because that number is expected to change from time to time, therefore the number becomes a random variable. So finally, when you're talking about modeling rates, proportions, percentages, anything that lies in the range of 0 to 1, we're actually going to use a beta distribution. Okay? Now, there are two parameters in a beta distribution. The two parameters in a beta distributions, they are alpha and beta, and the two of them represent shape parameters. Shape. And because, let me tell you this, if you really want to know how flexible is a distribution, it depends on the number of shape parameters. Okay? Shape parameters. Okay, so in a beta distribution, where you have f of s, okay, x raised to power this, 1 minus s raised to power this, divided by b of alpha beta, okay, where s lie between 0, 1, then your alpha greater than 0, your beta also greater than 0. If I want to rewrite this distribution now, don't forget, I told you the other time, I can write this guy in a non-integral form. Now, if I want to rewrite it, I can, give me 1 second. Let me test all the the markers here today. They are not writing fine. Please, if you cannot see, just let me know, okay? Okay, now I can write this as this. What have I done? Writing this in a non-integral form. Then finally, that's another way to write a beta distribution. Okay, now I think I just told you what we use beta distribution to model. Let me tell you this. If you don't have the idea, we normally use this beta distribution as a prior information, a prior probability distribution in Bayesian analysis. Okay, for instance, if alpha equal to 3 and beta equal to 5, maybe we're working on vaccination rates, okay, of a government. I remember during the COVID, okay, it is not 100% of the population that will be vaccinated, okay, and the vaccination rate is going to change depending on the campaign and the awareness, okay. Now, do you know if that followed beta distribution, okay? Now you know what this guy is trying to tell you now. You know what this guy is trying to tell you, the mean and the variance. He's trying to say, if we know the parameter to be this and this, okay, expectation of x is this, which is going to be this. Now, maybe 0.625. Now, he's trying to tell you the vaccination rate is, let me say, this should be less than 50%. So what is 3 over 8? Can somebody give me the figure? 3 over 8. What do you get? That should be less than 50. 0.3. Okay. Now, it's trying to tell us at the moment, on average, vaccination rate is 37.5%. This is a random variable. It can change. Okay. Now, what I'm going to show you now, and don't forget whenever average is involved, variance also needs to be involved. Now, what I quickly want to show you now, before I move to something else, I'm going to show you how to derive the mean. And I'm going to give you a clue on how to derive the variance. Okay? But I need to first tell you the meaning of what we're doing. Okay? If you know why we're doing this, if you don't understand the meaning. Okay? Now, what I want to do right now, okay, I want to show the mean of beta distribution. Okay, how is the mean derived as this guy? Okay, I'm going to write expected value of x. Okay, don't forget, this is a continuous random variable, 0 to 1, x, f of x, ds. You see that? Okay, you can see the state space, right? 0 to 1. Okay, now 0 to 1, x. What is the distribution? Okay, x raised to power this, 1 minus x raised to power this, then b of alpha beta ds. Any question? Okay, now I want to integrate with respect to s. I'm going to bring that guy out. Okay, so 1 over this. Okay, 0 to 1. We combine that guy. Okay, this. You see that? Can somebody tell me this for extra credit? In a beta, you want to write this guy this way. Can somebody tell me? Give me one. Let me write it very well. I want to write this to look like this. Can somebody tell me what to write using the idea of a beta function that I gave you before? Okay, let me do this. Let me write this very well so that you can see. Now, recall from beta function, b of alpha comma beta is this. Okay, from a beta function, this can be written as this. Can somebody tell me how this, if I want to write this to look like this, what am I going to write for extra credit? From a beta function, anything like this can be written as this. When there is alpha minus 1 here, there's going to be alpha. It's like adding 1, adding 1. Now, take a look at this. I want to rewrite this to look like this. How is it going to be? Can somebody tell me? Go ahead.
Alpha plus 1 and b.
Exactly. Send me a message for extra credit. Good job. Yeah. So this guy is going to be b of alpha plus 1 comma b divided by this. You see that? With the idea of a beta function, I've already skipped rigorous integration, calculus. You see that? Now, I now want to work with this guy. If I want to work with this guy now, you know what I'm going to be doing, right? I need to know the non-integral definition. Now, let's take a look at this guy. What is the non-integral definition for this guy? Gamma alpha plus 1 gamma beta divided by gamma alpha plus 1 plus beta. That is for this guy. Divided, what is the non-integral definition for this? Gamma alpha, gamma beta, gamma alpha plus beta. Any question? You know what I'm going to do next? What I'm going to do next is going to be super cool. Okay? What I'm going to do next is going to be super cool. Now, expected value of S equal. Okay? Now, if you take a look at this, I can rewrite this as right? 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 I can see that, right? Now, let's take a look at this guy. Now, E of S equal, instead of gamma alpha plus 1, right? Gamma alpha plus 1 can be alpha gamma alpha. Okay? This guy, alpha gamma alpha. What about this guy? That can be alpha plus beta, gamma alpha plus beta. Don't forget, gamma 7 is 6 gamma 6. Right now, we got this over that. Okay? Gamma alpha plus beta divided by gamma alpha. Let's see. What do we have? That is that. That's how to prove that the expected value of S equal to that. Okay? Now, if you want to, I'm going to quickly give you the clue for the variance. If you want to prove the variance, you can also going to make use of this. Okay? Right now, you need this guy. Okay? This already decided for you. You need to work on this guy. You see that? And that will take you to